Hi, this is Doug Malchow. Welcome to the Sensors Unlimited booth at DCS 2017. We've been asked to give a little background on why SWIR, why to use it for various applications. So we're going to go to present a slide deck and address those questions for you. Again, welcome. We've relocated for the convenience of looking at these slides. Why the SWIR band, why it's used is the intent of this talk. And I've blown up that chart to give you a good perspective of the different wavelength bands in the infrared. So we have on this axis the wavelength in microns. Notice that it's nonlinear, it's a logarithmic scale. So this is compressed relative to here. We have the visible band, the SWIR band, the near band would be here, I don't have a label there, midwave and long wave. On the y-axis we're comparing quantum efficiency. Quantum efficiency is basically for a given number of photons how many electrons are yielded. So it's a percentage type of yield. And we have various detector technologies illustrated, starting with this blue curve is a intensified photocathode tube. It's got low quantum efficiency, but it is very sensitive because it has large amplification. Your standard CCD, back thin CCD, has a response like this. Middle percentage range folds over, starts dropping because silicon becomes transparent at longer wavelengths and is actually used as windows. Then we start with the in-gas formulas. Our main formula is this red curve. The gold curve is what we call Viz in-gas. Gives us some response out to 500 nanometers. So a couple different solutions. These are extended in-gas for longer wavelengths, and then we have the mid-wave and the long wave. So that gets you oriented. And one of the things to keep in mind is that ordinary glass starts falling off around 2 microns, and high quality quartz gets you out to 2.5 microns. Those are important considerations, particularly when you start talking about thermal measurements, which are typically mid-wave, long wave. They can't see through glass, and that has important implications for some of the applications. So why do we want to use SWIR wavelengths? And one of the principal things that dominates many things is the longer wavelengths penetrate obscuring layers. This helps us in things like fog, because the small particles scatter short wavelengths very strongly. As you transition to larger molecules, longer wavelengths, medium particles only affect wavelength linearly. So we have this very good advantage to imaging relative to visible cameras, but only a mild disadvantage mid-wave and long wave. And in some cases over water, shortwave has advantage over mid-wave. And then finally, larger particles scatter all wavelengths. And so ultimately, nobody sees through heavy smoke or fog, whatever waveband you're using. Another principal driver for using SWIR wavelengths is that molecular vibrations absorb characteristic, unique signature wavelengths. And so that can be used to remotely detect the chemistry of things like pharmaceuticals, plastic recyclings, separating trash out from agricultural leaf products that are being harvested. Has an advantage compared to FTIR, which is used in midwave, that there's rarely any sample preparation needed. So SWIR is very adaptable to the industrial sorting process. Other niche applications, semiconductor band gap, because the silicon becomes transparent, You can use SWIR cameras to inspect silicon solar cells and ingots and other things like that. We're more robust and less costly than mid-wave and long-wave solutions. Fiber optic communications use our wavelengths very strongly, and so we're used for alignment and inspection there. And then you can have some non-interference with visible cameras by using us at the same time as regular machine vision cameras. This slide illustrates the penetration that you can get with SWIR in haze, the visible camera. This is all very cloudy. Here you see very sharply, 20 kilometers away, the mountaintops. Also notice that here you barely can see the clouds. Here it's very distinct. And the clouds are an example of some heavily scattering. Ultimately, I can't see through the clouds, and very few things can when they're dense enough. And very few wavelength technologies can image through clouds due to the large particle size and density scattering all wavelengths of light. Next, we're going to talk about the two major industrial segments that SWIR serves. Imaging, generally observing a scene to make an image, or spectral imaging, looking at multiple wavelengths to conduct an analysis. In general imaging, we can be used for thermal analysis, for hot metal processing, metal coatings, furnace monitoring to recover chemicals. Many times thermal cameras can't be used because the safety glass blocks them. In hot bottle glass processing, we're used because we can see inside the bottle to find a defect that a thermal camera won't. In machine vision inspection, we're used in many applications for agricultural, pharmaceutical inspection, semiconductor inspection, silicon solar cell, electroluminescence, and even imaging through solid silicon. A lot of times we're used to detect coatings that visible cameras are unable to see because they're transparent, or we're used to see through an opaque coating that a silicon camera cannot penetrate. And then, as we said earlier, imaging through haze. In spectral imaging, which can be hyperspectral, multispectral, or even just one or two wavelengths, we're used in a number of the applications just mentioned in machine vision, but also a special case for biomedical called optical coherence tomography. In this case, the tissue itself is very scattering, and we can be used to analyze the spectral characteristics of an interferogram to deduce the structure underneath the tissue surface. It also has an application in industrial film thickness measurement. In telecommunication, the data is flowing at 1310 or long distance at 1550 nanometers, and you have multiple wavelengths of light on the same fiber. In-gas SWIR sensors are used with spectral dispersion to see the individual wavelengths, check their wavelength accuracy, and monitor the signal to noise to the background amplification. In sorting, as mentioned earlier, for plastic recycling and agricultural grooming of bad materials, getting in with the agricultural leaf product, many times a spectral characteristic is used to recognize good material from bad. And then general spectroscopy for scientific investigation. So that gives you an idea of why and when you would use SWIR. Thank you for watching and paying attention. For more information, you can see a lot of these things illustrated on our website at www.sensorsinc.com, or you can contact us either at our email address, suinfo@utas.utc.com, or call us at 1-609-333-8200. Thank you and have a very good day.